We're very happy to have Ian Moult from Berkeley. He's going to talk to us about hunting for heavy winos at the Galactic Center with effective field theory.
Yeah, thank you very much for the invitation. It's very fun to visit. So today I'm going to talk about some work we've been doing in a number of papers on developing an effective field theory for indirect detection of dark matter, which is a bit hard to see here, and experiments such as this as shown here. And so this is done in collaboration with a fairly large, or subsets of this fairly large group of people. And so part of the reason for this is it has kind of people on the pure EFT side, and over here, more some kind of dark matter theory people. And then we also have actual Hesse experimentalists to help kind of tell us what exactly is needed on the calculational side. And also, it allows us to do actual forecasts with their full simulation machinery. And so I'll try and go through the kind of full story of this, but I am very much on the effective field theory side, and so I'll give kind of an effective field theory centric view of the whole story, which is why it's in the title. Okay, so as everyone here obviously knows, and so I won't dwell on it very much, so there's overwhelming evidence for dark matter, with the kind of canonical examples being, for example, the bullet cluster or rotation curves. And on the particle physics side, what we have are an extremely wide range of models covering a huge range of mass scales. And so there's now large experimental efforts to kind of search for and exclude or discover dark matter at all these different scales. And so in this talk, I'm going to restrict to things that are kind of very vanilla from the dark matter model building side, namely just WIMPs. And by WIMPs, I just mean something kind of 100 GeV to 100 TeV scale. And so, again, as everyone knows, so WIMPs are a kind of very economic or simple option for dark matter, and they're often motivated, for example, by SUSY models. And so, for this particular talk, the details of the model don't really matter at all for the setup we're developing. The only thing that matters is, for example, in numerical plots, I'll have to choose a concrete model. And so, the kind of benchmarks which are often used are, for example, the pure thermal wino, pure thermal Higgsino. And so these, if you demand the relic density, so they have one single parameter, and if you demand that you get the correct relic density, you get, for example, 3 TeV for the thermal wino, or 1 TeV for the Higgsino. And so these are just kind of the mass scales to keep in mind. And so this talk, whenever I show kind of actual results or forecasts from the experiment, I'll be using the case of the pure thermal wino, but everything can be done for essentially whatever model you want. So despite being the kind of one of the canonical examples of dark matter, these pure wino and Higgsinos are actually surprisingly hard to access at Collaborators or in direct detection. So this is just a particular plot for the monojet wino limit. And you can see this is shown here for a 14 TeV LHC, and then a forecast for a 100 TeV collider. And so you can see that even at a 100 TeV collider, you're probing something around, say, 1 TeV, and this is much lower than the 3 TeV thermal relic benchmark that you would kind of like to get up to. And so at a collider, this is extremely hard. And you don't get much better luck if you try, for example, at direct detection. And so this is just the cross-section. And so again, if you look at 3 TeV is somewhere up here, it's kind of right at the neutrino floor. And so this is, again, very hard to probe directly. So fortunately, one way which you can probe very high mass dark matter is through annihilation into photons. So you can consider the annihilation of, for example, 2 winos shown here into a photon and something else, for example, another photon, and you observe one of the photons at some detector on Earth. And so in reality, they produce these huge kind of Cherenkov showers, which are then detected by these kind of very nice detectors. And so this one that we'll use, or which our collaborators are on, is this Hesse experiment. But there's a variety of other ones, for example, CTA or Veritas, which are also ongoing. So there's a kind of fairly big experimental effort right now. And so these can probe dark matter from the kind of 100 GeV scale all the way up to, say, 20 or 100 TeV. And experimentally, this kind of photon lines provide an extremely clean signal that they can use to look for dark matter. Okay. So as is being pointed out in papers probably now 5 or 6 years ago, these line searches put extremely strong constraints on TeV scale dark matter. So this is just kind of our plot of this. You can see here is our kind of prediction for the cross-section shown in blue, with this thermal wino line shown here, and you can see the limit from Hesse shown here. And so you can see that at the region of kind of 3 TeV, where the thermal wino, you're excluding by kind of over an order of magnitude. And so because of this, one might ask why one would want to kind of work on developing techniques for, or an EFT for better calculating wino annihilation at indirect detection experiments.
Sorry, what is this prediction?
So this is just our prediction, which
You'll explain it later.
I'll explain how we obtain it later. But at this point, it doesn't matter, for example, if I move by a bit. The point is that if
But it's the peak is not where the thermal wino thing is, and there's this other peak.
yeah, so I'll explain the
You'll
structure of
explain
why,
all
as a
that.
function of mass, it has these peaks. But so as a function of mass, it will have these particular resonances.
Yeah.
And then this is just the thermal wino value is at 3 TeV, so it doesn't have, the thermalness has nothing to do with being at this peak of the resonance of the annihilation. Yeah. And so in this region, you're kind of excluding the particular thermal wino by a huge amount, and over most of it, you're excluding the wino. And so this will be pushed even further by future experiments. But so part of the question is, if you're excluding it by this much, kind of why bother improving the calculation? And so our main motivation on this is that all these limits can be easily evaded by modifying the dark matter density profile, for example, by coring it. So if you take, for example, some ionosphere profile, which looks like this, you can just cut it off at some value, which I'll call coring it. And so this is just a plot of these limits as you change the core size, shown here. And so you can go from, for example, this ionosphere here, and you can change by several orders of magnitude just as you change the core from essentially being no core up to something like 5 kiloparsecs. And so the thing that's more interesting now is that we're in a regime where the limits probe core sizes which are comparable to what's coming out of simulations or some very weak observational constraints from galactic surveys. And so if you want to actually kind of interpret reliably, both as a constraint on the particle physics cross-section, simultaneously with, or putting input on what is reasonable on the dark matter profile, then you actually need to have in your calculations factors of a few correct. Because, for example, if I'm off by a factor of 5, and I can go from having a core of something like 3 kiloparsecs, which is reasonable, to something like 15 kiloparsecs, which is something that is completely unreasonable and one should otherwise rule out. So if one actually wants to do this kind of robustly, take into account kind of astrophysical measurements, which can constrain the dark matter density, then you want to be able to perform calculations which are at least good to factors of, say, a few. Okay, so why is it hard to get calculations which are good to factors of a few? Which may seem kind of very easy for electroweak perturbation theory, but it turns out that it's not, partly because of these large structures which you pointed out earlier. So if you consider something even as simple as the exclusive 2-to-2 scattering of 2 of these winos into, for example, 2 photons, you'll find that you actually get a number of quite interesting effects because you have this extremely large hierarchy between the electroweak scale, which I'll always just denote as MW, and the dark matter mass scale, which is, say, up to 100 TeV. And so in particular, in this fully exclusive process, you have both this Sommerfeld effect, which is giving powers of this alpha W times m chi over mw, just to some power k. And so this is what will lead to these extremely strong peaks once they're resummed. And you will also get, and so these come from exchanges of kind of very light from the perspective of the dark matter, W's or other electronic particles in the initial state. And then in the final state, where you have these kind of massless, highly moving particles, or massless from the high scale, here you'll get Cherenkov double logarithms, which again have a large effect. Instead of being powers, these are alpha W times log squared, again, of this ratio. And so, if you want to have
what are you exchanging between the photons?
So,
it's like green with blue line.
Yes, so here, this can be like a W, for instance. So these pictures are a bit, because it depends whether you're on the broken or the broken, and you'll have things changing so as to make it real. But I'll show the actual, these should just be taken as schematic and don't necessarily make, exact sense as is. Yeah. And so this kind of, what can be referred to as this fully exclusive line cross-section, has been analyzed by these groups that we were discussing earlier. And so this could be done entirely using kind of already known effective field theory machinery. So in reality, if you go talk to, for example, the Hesse experimentalists, or if you think about it a bit more, what they actually need is something much more complicated. So the Hesse experiment is kind of on one side, and so you detect one of the photons. So you do not detect whatever else is going the other direction. And so what they actually need is the kind of spectrum of the energy of this photon that they will be observing in the annihilation. And furthermore, because these are coming from large showers, right, their energy resolution isn't extremely good. And so what they're kind of doing is smearing effectively over this region near this line and cross section coming from the back-to-back photons or Z. And so what we'd like to do is to compute this, which, as I'll explain, requires a kind of significantly more involved field theory setup. But this is the kind of thing that's actually needed from the experimental perspective if one wants to have kind of realistic calculations that are good to an order of, say, 1 or 2. Sort of 1 or 2 factors. Okay, and so this is the kind of motivation for the rest of the talk. So I'll begin with a kind of overview of the, kind of slightly more precisely, the kinematics for these indirect detection experiments such as H.E.S.S, and discuss the effective field theory which are used to analyze these limits. Then I'll derive, I won't derive, but I'll explain what is meant by a Factorization Formula, and then want to kind of explain how it can be used to compute the photon spectrum in H.E.S.S. And then I'll actually go through kind of putting these into the H.E.S.S forecast and discuss some constraints one can derive on the core size and some kind of future analyses which they can do based on these results to better probe the core. As I said, these two are based on kind of fairly technical stuff, and so what I'll mostly try and do is just an overview of, for example, why we do what we do, why it works, and then this one will be more the kind of phenomenological results. And so if anyone has any questions throughout, just let me know. Okay, so first, we're going to just go through the kinematics and effective field theories for these indirect detection experiments. Okay. So slightly more formally, what we're interested in is we want to consider the annihilation, for example, concretely, of these two winos into a photon plus x, and x is everything unobserved. So the photon goes into the Hesse detector, and I have no constraints over everything else. And so it would be useful to use the dimensionless variable z to characterize the final state. So z can just be defined as the ratio of this photon's energy to the dark matter mass. And so if you go through a little bit of algebra, you can also show that it's 1 minus z is the ratio of this invariant mass squared of this final state over the invariant mass squared of the initial state. And so essentially what it's doing is measuring how much kind of mass there is in the final state. And so just to kind of show in pictures, so Z measures in some sense the additional radiation in the final state. So if you go into exactly 2 back-to-back photons, you have Z is exactly 1. As you start to spread away from that and get some additional radiation along these directions, or some low energy radiation in the event, you kind of move away from 1, and eventually if that particular photon that you detected was nothing special and just some kind of part of a giant mess of photons, then you have this 1 minus z is approximately 1. And so from a just field theory perspective, or just to give an overview of what's known in the literature, so these exclusive and inclusive cases are what turn out to be easiest to analyze from an effective field theory point of view. And this is the one that will ultimately end up being relevant for the experiments, which we'll have to understand how we can analyze it. Okay, so if you're an experiment, or if you have an experiment like H.E.S.S, what is actually relevant? So ideally you'd like to perform a line search, so you want to kind of get yourself into this fully exclusive region. But because you only constrain one of the observed photons, you cannot fully constrain what's going on in the rest of the event. So if you can only measure this photon, and if you knew the mass of the state, to constrain that there's actually no additional radiation in the event, if you wanted to fix it to the example there's only a single Z, you can't radiate, for example, another Z, at a mass of, say, 10 TeV for the dark matter, you'd have to measure Z to, say, like 4 digits to constrain that there isn't an additional Z produced in the event. And so this is obviously not what's done. And so instead, what Hesse is actually doing is averaging over some kind of region near this exclusive endpoint. So they typically have a kind of resolution which is equivalent to a Z of, say, 0.85, and they're just kind of averaging over this complete endpoint when they do their searches. And so what you have is not a kind of fully exclusive 2-to-2 process, but you have a nearly kind of exclusive, but with some additional radiation in the final state. And in particular, you have what's known as a jet, which is radiation constrained to be along some particular light-like direction. And so just to make this kind of slightly more precise, so for a small Hesse resolution, 1 minus Z is small, and so 1 minus Z is just related to the mass of the final state. And so if you have a very small mass, there's 2 ways that you can do it. So if the mass is small, your radiation can either be massless, collimated along some particular direction. And so if you just work this out, you can have an angle which goes like the square root of 1 minus Z. Or the radiation in the final state can be soft. And so again, if you go through a bit of algebra, you'll find that the ratio of the energy of, and by soft I mean low energy, of this soft particle over the dark matter mass scales like 1 minus Z. So as you let 1 minus Z goes to 0, you essentially pinch both the angle and the energy of any extra emissions to go to 0.
Sorry, to make sure I understood. You said it has CZ of 0.85. I would have thought it would see Z bigger than 0.85. You're saying it's smaller?
No, so they look
sensitive to which side?
Yeah, so they're 1 minus Z going to, so they're sensitive to this. So Z going from like 0.8 to 1.
So, but then why are you looking at, okay, yeah.
Yes, it's a bit confusing because I flip between 1 minus Z and,
right.
Yeah.
No, that's fine.
So I'm going to look near to this fully exclusive region.
Right.
And so effectively what this Hesse resolution is doing is to force you into these soft and collinear limits for the final state. Okay, so just to summarize this. For this heavy WIMP annihilation, what it's effectively doing is it's producing a jet, shown here, which recoils against the photon which you observe. And so this jet is this spray of collimated, in this case, electroweak radiation. And so what Hesse is doing is measuring this energy spectrum in this region. And so in addition to all these problems which I showed earlier, as soon as you have a jet with some kind of resolution variable, what you get are perturbative Cherenkov double logarithms of this alpha W times log squared of 1 minus Z. And so if you want to be able to compute this spectrum and get something that is finite, you need to be able to kind of resum these to all orders to get a smooth spectrum like is shown here. And so, as I mentioned earlier, these previous approaches have only computed, they just given, for example, a delta function at the endpoint, and don't discuss this spread away from the endpoint. Okay, so hopefully I've convinced you that this indirect detection is a fairly complicated multi-scale problem. So in addition to the ones which I showed earlier, namely the Sommerfeld effect and this electroweak pseudophils, you also have these resolution effects. And so you have this whole host of kind of different scales. And so this is something which is kind of ideal for an effective field theory or factorization treatment, which will essentially allow you to break this up into kind of simpler and more tractable problems. And so just to kind of, so one thing you might expect is because alpha W is extremely small, that these are actually not kind of problematic effects. But just to kind of show that they do have very numerically large effects. So this is a bit hard to read here, but this kind of curve which goes like this is if you just compute at one loop. Right, so if you do this, first of all, it's hard to do the full electroweak calculation at one loop. And second, you get something that looks absolutely nothing like the full results. And so it doesn't matter what all these other kind of curves are, but the only point is that they're all giving results which are differing by easily factors of 10. Even when they're just different, or they're just due to these alpha W suppressed effects. And so essentially what one has to do is to just understand how to kind of disentangle and reorganize the perturbative expansion. And so once this is done, you should have an extremely convergent series in alpha W, and you won't actually have to calculate to very high orders. So you just need to kind of reorganize it and set it up in the correct way, and then it will converge extremely rapidly, and you can just easily compute the spectrum. Okay. So the way we'll do this is to use the approach of effective field theories, which essentially will allow us to focus on kind of the relevant degrees of freedom for this problem and integrate everything else out, which is more complicated. And so this is particularly convenient in these problems where you have a ton of different mass scales, which make doing an actual calculation extremely difficult. And so in this particular problem, we have kind of argued that the relevant degrees of freedom are these collinear and soft degrees of freedom, and that everything else will integrate out and fall apart. And so there is an effective field theory for long wavelength dynamics of soft and collinear radiation in the presence of a hard scattering, and this goes under this name of this soft collinear effective theory, which was developed by these people here. And it was extended to the electroweak theory by Anish Manohar and Collaborators. And so I'm not going to go through any technical details of SCT, other than the kind of a very big scale picture, but the only thing that one needs to know to understand how to kind of, or to understand the language, is that in SCT one has different fields for these collinear and soft modes. So you have a kind of collinear gauge boson and a soft gauge boson. And so you really think about these as kind of different fields in your Lagrangian. And so the reason, and so SCT, at least at its kind of base, is no different than any other effective field theory. And so it was originally developed in the context of QCD scattering, which is why I have this kind of fairly complicated picture. But so all one does, just like any other EFT, is you first perform a matching calculation onto some operators in the EFT. So you take some very complicated process, you match it onto some, with many, for example, jets, you match it onto some operator which has these different fields in several different directions. And then all the long wavelength dynamics of the soft and collinear modes, which are in these jets, is just described by the Lagrangian of the effective field theory, which essentially just dresses all those operators and produces jets. So these you just calculate in the effective field theory like you would in any other effective field theory. So what makes SCT useful is that when you have soft and collinear gauge bosons, they can obviously interact. So if I have some collinear particle shown in blue, it can emit green radiation, which is soft. And it turns out that in the effective field theory, one can perform a field redefinition at the level of Lagrangian, where you take your field and you multiply it by a Wilson line along some particular direction of the jet. So this is in the adjoint for the gluon, and in the fundamental for the core. And so if you go through this exercise of doing this field redefinition, you'll find that the Lagrangian and the states exactly factorize into fields that no longer talk to each other. And so effectively what you've done is you've taken some kind of particle which is emitting a whole bunch of soft radiation, and from the perspective of the soft radiation you replace it by some Wilson line along the direction, and then there's no more interactions between the soft and collinear fields.
So you don't have any states which are both soft and collinear?
Sorry?
There are no states which are both soft and collinear?
In this, so
Because it's
it depends on the problem, and you definitely can. In this particular case, although I will completely gloss over it, there are ones that are soft and collinear, but in many problems you don't have ones that are soft and collinear. And you have to remove the overlap between the two. So often this soft collinear region is kind of scaleless, and if you do it in pure dim reg, it just removes itself. But in a more general case, you do have to treat it. Yeah.
Is there something interesting that happens from the Higgs and the longitudinal gauge bosons?
I mean, not super much from the effective field theory point of view. I mean, you should kind of treat them more properly, but not really. Let's say, yeah. Good. And so the reason why this is kind of useful is if you have some cross-section which you want to compute, you can break it up into different pieces which you can calculate separately. So since things no longer interact, if I have some cross-section, for example, for producing some jet as a function of this kind of energy which I showed before, I can write it as some kind of piece that I've integrated out, which is just some factor, times some piece which is called a jet function, which describes the collinear dynamics, and a soft function which describes this soft radiation. And in general, there'll be some kind of convolution between the two which describes how they share some particular variable. This is just kind of very schematic. And so once you've kind of broken it up into these separate pieces, these are often by themselves much easier to compute and just kind of makes your life simpler. And so this is particularly true in these kind of multi-scale problems, because essentially what the factorization allows you to do is it allows you to break up the cross-section into a product of functions, each of which depend on a single scale. And I'll explain what that means a bit more in a second. And so once you've done this, each of these functions can be computed in some kind of expanded limit, where it's often essentially trivial to do so, at least at the low orders that will be needed in this project. And then all logarithms, which I discussed before, which are problematic, can be resummed by renormalization group evolution of these different factorized functions. And so I'll explain in a second what exactly this means. And so if you can do this factorization into a whole bunch of pieces, it offers a very powerful approach to these multi-scale problems, like the one I discussed, which has a whole ton of scales. And so just as an aside for people who don't often think about these, so when I said single scale functions, so if I have a function using GMX, so if I have a scale mu, and if I have a function which depends on a single variable, for example this m chi, then when I compute it perturbatively, the only thing I will get in these limits is logs of mu over m chi. So I can have something like 1 minus alpha w log squared of mu over m chi. But once it's single scale, that means that at this particular value of mu equals m chi, I just have a well-behaved expansion with no logarithms, with just order 1 numbers times alpha weak. And so in particular, in electroweak perturbation theory, these are truly very small. And so these things that I showed earlier, these like angular scalings in terms of z, are just the natural scalings of these different collinear or soft modes. And so what one can do now is one can take this function, evaluate it at this particular scale, where it has no logs, and I could run it, for example, to the scale mw. And so it will obey some RG evolution like this. And if you run it to the scale mw, you'll just get an exponential of these logs, and so we'll resum it to all orders. And so if you can successfully break your problem up into all these little pieces, then you can just very easily resum them like this. And so it kind of gives a way for treating these complicated multi-scale problems. And so although I won't go into it in any detail, so the standard SCT cases which were developed either to deal with some constraints on massless final state radiation, like this energy, or on virtual corrections for these massive gauge bosons. And our situation is kind of significantly more complicated because we have constraints on massive final state radiation. And so you have to simultaneously consider effectively these two scales, namely the constraint of this resolution coming from the Hesse measurement and the fact that your gauge bosons have mass. And so although I won't go into it in any detail, this relates to Yaroslav's question, and essentially what you get are these modes which are a mixture of soft and collinear. And so this is where the techniques to deal with these were developed along with some collaborators in the context of jet substructure. And so though this is kind of a bit of a hand-wavy thing, so in jet substructure you're often interested in measuring both like kind of a mass of the total jet and then some additional measurement on the internal structure of the jet. So you again get these problems where you're measuring, or you're making effectively two measurements. And so from a mathematical perspective, it turns out that it's exactly the same situation as we need in this electroweak case. And so we'll just kind of port over the techniques which were developed here. And then so the final ingredient which is needed, and I won't discuss it because it's kind of being more well developed, is the incoming state is kind of these extremely slow moving particles, and so they can be treated using non-relativistic effective field theories. So as with the final state, all the interactions can be decoupled using these field redefinitions into Wilson lines, and you'll get your standard non-relativistic Lagrangian. And so these Sommerfeld effects, which gives these large kind of peaks, which are shown here, are described by matrix elements of some particular states. And you can take different ones and they'll appear in particular linear combinations, as I'll explain later. And so these can be mapped just to standard quantum mechanics problems, which you just solve numerically to get these Sommerfeld factors or to get these Sommerfeld factors, and they can be combined in particular ways which appear in the factorization formula. And so these resonants, which are shown here, you can estimate that they kind of appear as essentially multiples of this alpha W m chi over mw. But they're not related kind of to the thermal story in any way. They're just related to the particular masses of the gauge bosons which are being exchanged. Okay, so this kind of sets up all the formalism, which is admittedly quite a bit, which is required to treat these pieces. And so now we'll just discuss, kind of in a very hand-wavy way, how one puts them together into what is called the factorization formula to actually be able to calculate, for example, the photon spectrum at Hesse. Okay, so as I discussed, what you want to essentially do is to break the problem up into a whole bunch of different pieces, each of which depends on a single scale, and then you can use RG evolution to some common scale to put them all back together. And so because of all these different scales, the resolution, the electroweak scale, and this high scale, you end up getting a whole ton of these functions, but you can still just go through it. It's ultimately kind of a technical exercise, so I'll just kind of schematically describe the final results. But essentially what it gives you is a kind of factorization formula for this cross-section in terms of a whole bunch, in this case I think 7, of these single scale functions which you need to sew together. And so each of these describes some particular dynamics at a given scale. And so just kind of very intuitively what they kind of describe. So as I discussed before, one will have these kind of hard dynamics, which are these kind of virtual corrections to the hard scattering process, which need to be integrated out into some matching. You'll then have some functions which are essentially matrix elements of these Wilson lines. And so if you're not familiar with this notation, this cut. So here you're computing a cross-section, so it's essentially a squared matrix element, which you can draw by rotating across a kind of cut in the center. So it's like an amplitude times the amplitude conjugate. And so these are just matrix elements of Wilson lines, which just kind of trace out this 2-to-2 process. And you have pieces both at the electroweak scale and effectively massless pieces. And you also have pieces which describe your kind of final state jet, both pieces that describe the kind of mass pieces of it, and pieces which describe the massless pieces of it. Yes?
I just asked, so you have these 7 functions.
Yes.
So if there is some like combined perturbation theory, or how do you do it? If each of them you calculate separately
Yes.
to some order,
Yes.
and then you put it together, so you
Yes.
kind of combine different orders from different functions?
Yeah, so you
Or-
expand it, like if you compute them, for instance, you can compute them each to like alpha S, and then when you multiply them together, you just keep the full answer to alpha S.
Okay.
So-
But you have to calculate each of them separately to kind of the maximum order.
Yes, exactly.
So there is no
But
shortcut. Or
no, but so at the level that we're doing here, right? So because it's like electroweak perturbation theory, you never actually need any of the corrections. So like all these functions at their natural scale are like 1 plus alpha W.
Yeah.
And then everything else you can get from resummation.
Okay.
So in the electroweak theory, you can just, they're all 1. And then all you need to know is they're an almost dimension. So you actually, like, at the order which is needed for any kind of reasonable precision electroweak theory, especially for this problem, all of these functions at tree level, they're just like 1, 1, 1, or, I mean, they can be normalized to that, and then you just need their anomalous dimensions, which kind of resums things. But in some, like, for example, in QCD, if the Coven constant isn't this big, then yeah, you just need to compute them all. But most of them are they're essentially trivial to calculate even at one loop because they're just like iconal factors. So once you've broken it up, each of them is very simple. Whereas if you actually try and do an exact calculation with kind of massive gauge bosons with constraints on the final state, you can't do it in closed form.
So which one has the Sommerfeld?
So the Sommerfeld, I will attach, the Sommerfeld will be reinstated in a few slides. Yeah, so this, although I've been a bit So this piece, these Sommerfeld factors, essentially pull out into an overall normalization associated with the initial state for particular color channels, and then you just tack them back on. So this formula I've given here is quite schematic because it's really a sum over different pieces, and so I'll show at a given accuracy how it actually looks with different Sommerfeld factors in a second. Yeah, so this is just kind of, so there's like tensors, and it's just meant as kind of schematic. But it's effectively just broken up into these pieces, and then the Sommerfeld, which will be tacked on to the beginning. Okay, so then, as I discussed, you can now just put these together so everything's effectively one at this order, and then you can just use resummation to generate all the logarithms. And so it turns out that this resummation is in a kind of complicated two-dimensional space, but you can just run them all to some position that you like, and schematically it's just doing this standard RG evolution, like for the beta function that everyone is familiar with. And so because the logarithm is kind of a pain, but if you kind of do it, at least at, for example, the lowest order, you get essentially a very simple kind of one-line formula for the spectrum, for the photon spectrum as something like Hesse. And so this, and I'll explain it in a bit more detail the different pieces, but essentially is a kind of line piece, which is a delta function localized at the end, and then it's a kind of 1 minus z power law modified by some effectively logarithms, which shows the decay from this endpoint. And so it's a combination of these perturbative logarithms, which I'll define in a second, as well as these different Sommerfeld effects shown in orange, which I'll again give the definition for. And so you can go to the next higher order. It's just an algebraic exercise, and you get something which you can just write analytically instead of being a line. It's kind of a page, but it's not super interesting. And so just to kind of explain what's actually in this formula, so these this 1 minus z kind of power law is just modified by exponentials of logarithms, and so you have these logarithms associated with, again, these natural scales for both the collinear and the soft radiation, which are just combined in some kind of fairly non-trivial way. But again, it's just this very simple, essentially power law behavior. And the kind of more interesting thing is how these different Sommerfeld factors are combined depending on the particular radiation which is in the final state. So you'll notice that this line cross-section here, where you have these two photons, you get this purely of a single 0, 0 to plus minus Sommerfeld factor. But once you have these more complicated transitions in the final state, you get these more complicated particular combinations of, for example, this neutral neutral to neutral neutral, and neutral neutral to plus minus Sommerfeld effects, which are all kind of incorporated into this formula. And so you can now just kind of go ahead and plot it. So this is just the spectrum shown here, and all these will be shown both a leading log and then a next leading log, just to show that once you've kind of done this reorganization, you essentially have, very, very good convergence of your perturbative expansion. And so you can see that it has this kind of peak delta function at this endpoint where you have the fully exclusive, and it just describes this kind of 1 over 1 minus z decay away from this endpoint as you get more and more radiation. And so you can see that once you've done this resummation, and these error bars are, just shown here, are completely negligible once you've done this reorganization, so there's kind of no motivation to ever go beyond this. It's just simply an exercise of reorganizing things until they can be combined properly. And so, as I said before, what Hesse is effectively doing is integrating over this region. So you can just plot the kind of cumulative cross-section integrated over this region, which is kind of shown here. And so you can see kind of from this is you get some non-negligible contribution from these non-line photons. And so this is something which will ultimately be able to be used to kind of strengthen the limits from something like Hesse. But the main point from this is that you can just put in some realistic resolution function from the experiments, and actually uses or allows the kind of real experimental resolution to be used to make realistic predictions for what is required of the experiments. Okay, so now I'll move from the kind of EFT setup to the actual kind of forecast using the Hesse experiment. Okay, so with our collaborators, we performed this kind of fully realistic Hesse analysis using this prediction for the photon spectrum. And so when I say we, it's primarily our Hesse collaborators, which are shown here, who are able to use their kind of full analysis framework to actually go through and do a kind of completely proper job of this at the level of the experiment. And so part of the reason we did it as a kind of forecast instead of a recast of their data is if you're using their previous data, you don't have all the correlations. And so if you do it instead of forecast, but with the same amount of data, you can actually do a fully proper job of everything. And so what we just did is their kind of a reanalysis of their standard analysis of the inner galaxy. So just looking at kind of regions right about the center of the galaxy shown here. And so the goals of this were first to just understand the effect of having this proper calculation of the endpoint, and then also looking at using a wider region of interest to improve sensitivity to the core size, which is one of the things we wanted to probe. And so this is a kind of very quick review for people who haven't looked at this stuff in a while. So the flux of the detector can be written as some kind of normalized spectrum times a kind of cross-section, this sigma v shown here, and then multiplied by J factor. And so this J factor is this particular integral of the dark matter density shown here. And so what you can do with a measurement of this is to either constrain this sigma v, which is coming from the particle physics side, or you can constrain this J factor shown here. And so I'll do a little bit of both in the results which I show you. Okay, so the first and kind of most basic thing we can do is to just provide updated limits using our proper spectrum. And so this is just an update of the limits using essentially the amount of data that I have so far, of 250 hours. And so this, apart from the fact that it uses kind of the up-to-date cross-section, I mean, nothing really changes, and you're still kind of excluding the thermal wino significantly in this range. And so the one kind of interesting thing is that by including these additional endpoint photons from the exact shape of the spectrum, you can significantly kind of improve your limits, so from here to here, because you're properly incorporating essentially more photons away from the exact endpoint. But this is in some sense fairly minor because you're already excluding things by a huge degree. So the more interesting thing one can do is, as I mentioned earlier, one can reinterpret this as a core size constraint for a particular profile. So again, this is just this an astro profile, and the simplest thing we can do is just to core it at particular values. And so this is just some model for what one might expect. And so just as a kind of point of reference, so the kind of modern simulations typically give kind of flattened cores, which are well modeled by this, of order, say, 1 kiloparsec for Milky Way-sized galaxies. But there's some fluctuation, but just as a kind of baseline. And there's also some very weak constraints, which should be taken with a grain of salt, from stellar motion, which suggests a kind of core size for the Milky Way of less than 2 kiloparsecs, which is again just a kind of number to keep in mind. So if we now use our prediction to plot a fork or a constraint as a function of the core size for this wino dark matter, which is shown here, you can see that for a thermal wino, you're ruling out cores up to, say, for example, 1.5 to 2, depending on the exact, or within the uncertainties. Right, so this is now beginning to enter a very interesting region, since you have kind of additional constraints saying that it should be below, say, a couple kiloparsecs. And so this, as you can tell from this plot, the fact that one is able to probe so well, for example, the thermal wino, is because it's riding this kind of Sommerfeld enhancement effect. And this is something that I want to show here is much less true for example, the thermal xeno. And so this is very much beginning to enter kind of a really interesting regime where you have some increasing the precise astrophysical constraints, which are pushing the core size below a few kiloparsecs, and then these improving observations, which are now essentially matching right back up to them, and are very well controlled, which are also probing this couple kiloparsec core size.
Are you pretty confident that the position of those peaks is under control? I mean, it looks like, if you move that first peak
Yes.
over a bit, you make a big difference, right?
Yes, so it is under control, but I would say it is now the leading uncertainty.
That's the biggest.
Yeah. So going to improved accuracy at what we've already treated is essentially irrelevant at this stage, and the leading is correctly describing this Sommerfeld effect and corrections to it. Yeah. But to leading order in our expansion, which should be good, it is well described, but at this point that is the leading thing. And so just one kind of interesting thing. So if one is interested in primarily focusing on bounding the cores, one thing one could do is to extend the standard Hesse analysis to look at a wider region of interest around the galactic center. So normally they look at kind of 1 degree, but this can be expanded to 4 degree if your focus is on probing the cores. And so essentially what this is doing is getting essentially more photons from these highly cored profiles. And so to be able to probe them, you need to essentially expand your region of interest considerably. And so this is purely a forecast because this is something they haven't done but are excited in doing. And so if you look primarily, for example, at this plot here, you can compare their standard 1 degree analysis with 250 hours, which is what they currently have, to doing the same 1 degree analysis with a 500 hour exposure. And so you can see it doesn't improve that much in terms of this core size constraint for a thermal wino. But if you extend to, for example, this 4 degree region, you can now kind of fairly significantly improve the core size constraint. And so you can get out to something close to kind of 5 kiloparsec. And so if there's kind of astronomical measurements which are pushing you to around kind of in this kind of ballpark again, this is starting to put or stronger either tensions or at least it's probing it right at the boundary of what is allowable. So it's in this kind of very interesting region for actually being able to say something concrete and independent of the profiles for the thermal wino. And so just to conclude, so hopefully I convinced you that these effective field theories provide kind of powerful techniques for these multi-scale problems for systematically breaking them up and treating the logarithms. So I derived this, or I showed a factorized description for this photon spectrum in the endpoint as relevant for indirect detection experiments such as this H.E.S.S shown here. And then I kind of presented results from this H.E.S.S forecast. And so by using these increased regions of interest, this allows one to start probing cores all the way up to kind of 5 kiloparsecs, which is then becoming in kind of tension with observations of the core size from other measurements. And so this is kind of right on the boundary of what is very interesting. And so hopefully their measurements in the future will kind of allow one to say something concrete and independent of the particular dark matter profile modeling which is used about the thermal wino, and more optimistically something like the Higgsino. Thank you.
Questions for Ian?
I have this EFT setup question.
Yeah.
Okay. So yeah, maybe this is something probably completely basic. Just in the scat,
Yeah.
You separate these degrees of freedom, but
Yeah.
you kind of still use the original Lagrangian of the theory, right? Just separating these degrees of freedom. So there are no kind of corrections, let's say, to electroweak Lagrangian or QCD if you do it in scat. You will have nothing like corrections.
You do have, so in these separate pieces, you don't use the full, so like you break it up, for example, in the standard, if you just break it into soft and collinear,
Yeah.
then in the soft, what you're computing are like matrix elements of Wilson lines. And in the collinears, you can think about it as using like splitting functions.
Yeah.
And so they have been expanded. And so in these, there'll be corrections in the powers of the expansion parameter. So for example, there'll be pieces which are suppressed by powers of like MW over M chi in this particular case. And so these are being dropped.
Okay.
In some way, it's
No,
like
no,
you're
what
doing
I-
a
what I-
different kind of derivative expansion in
Yes.
each region.
Yeah, that's what I meant. So if you really do the splitting of degrees of freedom,
Yes.
do you need kind of include in principle some higher order operators to kind of treat the
corrections.
error. Or
Yes,
the correction.
absolutely. Yes.
Okay.
Yeah.
So you do have that.
Yes. And so, I mean, some of these are quite easy. So example, I mean, just the simplest case, if I do something like E plus E minus, like if I just have a source which goes into two jets, right? At leading order, I just have an operator which has one field in each direction. And then I have a Wilson line operator which is just seeing these two directions, and I just compute some expectation value of a Wilson line. But there'll be corrections of it where you have an operator that has two fields in this. And so this is like an operator, so this is something that's not created by like a splitting function. And so it's separate than having something like this where it then splits. And so this would be down by power of whatever you're computing.
Okay.
Yeah. But if you're in the region where these are valid, these should be legitimately suppressed. And so they're all suppressed by power. So like here, this is suppressed in this, at least this MW over MK. So these are suppressed by quite a bit. And so these are, I mean, admittedly, although the leading power, it makes it very simple. Computing these calculations or these corrections can be quite non-trivial. And so for something like this, it would be a complete mess to compute these.
And it's off topic, but I want to ask anyway. If the Sommerfeld enhancement, is it at all important or useful at a hadron machine when you're pair producing these things? So if the PDFs make you smear over the initial kinematics, right?
Yes.
But for example, you may be measuring the total energy in the event. You might,
Yes.
right?
Yeah.
And so you might hope that in something like this, some of this structure would help you extract the signal.
Yes.
Is there anything?
So I don't know off the top of my head of a hadron collider example, but definitely an E plus E minus.
Sure.
So if you do like E plus minus to
minus,
TT bar,
yeah,
is
and you would,
essentially the flip of this. And there it's been studied extensively. I'm sure if you're making some additional measurement, you can probably force yourself into a region in proton where it does. But I'm not sure of a case off the top of my head where I've seen it illustrated.
Yeah. I was wondering if one could use it to somehow extend the reach, say the 100 TeV collider, you might want to try to extend the reach for these things out there.
Yeah. But I assume if you could again do like TT bar production where you force yourself near to the resonance.
Right.
And then,
Exactly, that's the sort of thing.
yes. And so I think, I mean, I just don't know of an application where it's actually being used. But I think one could definitely force oneself into that region.
Any other questions? Let's thank Ian again.